Thank you, Ernest. So I'm here to take you through the journey that we had to get gRPC load balance for our services. And spoiler alert, we did it in Rust. So who am I? I'm Helge. I'm a Rust backend engineer at TrueLayer. I've been at TrueLayer since September last year, originally Norwegian, who moved to Milan. So today I'm going to talk first about what might be the problems that might arise with gRPC load balancing, and just the general solution space of how we might go about solving that, and what we did at TrueLayer to solve it. So why is it hard, you might ask? So first we have to understand that gRPC uses HTTP 2 as a communication protocol. Therefore, multiple requests are multiplexed over a single TCP connection, where it's very performant because you pay the cost of creating one TCP connection, and then you concurrently multiplex the request over that connection. And this makes them sticky, meaning that from a client to a server, you always want to keep that alive to have the best performance. This also means that it's per request load balancing, so it's not like when you have a TCP protocol where you open a connection, and when maybe the next time you do a request, you have to open another connection. And so this also means that load balancers that sit outside, if they're not implemented in the client, they have to sit outside, and they have to be able to tell requests apart, so that they're in the 7th layer of the OSI model, the application layer. So just to give an example of why sticky connections could be a problem. So here we have a proxy that sits between a bunch of servers and a bunch of clients. We have client 2 that wants to do a request, connects to proxy. The proxy sees the connection coming in, chooses server 2, and the connection is sticky in that way, so that all the requests that client 2 does will continue going to server 2. Now, this is very inefficient because it will only touch one server. So ideally here, the proxy has to be able to read what's going on, tell requests apart basically, so every time the client sends a request, it can balance that across the servers instead of maintaining only that connection between the two. There's also another problem that you might have, and so to take you through that problem, consider this toy system with one client that maintains 2 connections, one to server A and one to server B. Now, what happens if server A crashes? If server A crashes, the client is not able to talk to it anymore. And let's say here we're in some sort of infrastructure where we've set a bound on the amount of replicas, so the infrastructure spins up server C. Now, the client only has one connection open to server B, and it's not aware that server C has come up because it hasn't refreshed anything, and it doesn't become aware of that server C. So this leads to a very skewed load where the client only calls server B. And of course, if server B also goes down, there's nobody to call. So this has a couple of solutions. For example, the servers might force the clients to reconnect periodically, so that the client has to read the service name of the service containing all the servers to get an updated list and update all the connections that it has to all the servers. Or the client can, if load balancing is done within the client, it can periodically update that list of servers so this don't happen. Or you can introduce an application load balancer that takes care of most of these things for you. So let's just go through a bit of the options that we have to enable gRPC load balancing. So you have the client-side approach where everything lies with the client, and you have out of process. So these are the two kind of categories I'm going for here. And in the out of process, there's some or most of or all of the gRPC load balancing that has been taken out of the client. So let's start first with the client side. The client maintains n connections to n servers, and every time a request comes in, it chooses the server with the least amount of load and forwards the request there. And of course, here the client also has readiness probes to check if the servers are up, etc. Now, this can make clients very thick, a lot of complexity, and they're language specific. So if you implement it in one language, you can port it to another. The pro of this is that it's testable in the sense that you can have an integration test where you can assure that the client does the correct things when you have churn in your servers. It also has less overhead, meaning that you don't have an extra network hop as you have with a proxy, for example, and there's less moving parts. So moving to the out of process category, which is look-aside here, is the first one. And here, some of the logic is moved out of the client. So the thing that's moved out is the look-aside service takes care of figuring out the clients that are online at all time, does readiness probes, things like that. But then some of the logic also remains with the clients. For example, being able to talk to the look-aside service to have information on which service to call next. And they also have to maintain end connections to end servers. Then you also have the standard standalone proxy approach, where you kind of completely take the logic out of the client. This, though, gives the clients a very easy interface. It only needs to connect one place. All the requests that's sent to the proxy will be equally balanced across the servers that are there. Then you also have a kind of a different approach to the standalone proxy, where you have proxies that sit with each client process, also called a sidecar proxy, for every gRPC client that you have. Then the last one is kind of baked into your infrastructure, where the infrastructure takes care of the routing and the load balancing. So you have services that sit with your servers and your clients that takes care of this routing. Now, just to go through what might be bad with this, or what might be a bit better about this. One of the cons, for example, is that this adds complexity. You maybe run in an environment where you have a lot of complexity, you have a lot of components, and if you add one component to that, you're just adding more complexity, service you need to monitor, configuration files, etc. It also adds latency with this extra hop that you have to do before you reach a server. And also the last one, the service mesh, is very dependent on your infrastructure and very invasive to install into your infrastructure. The pros, though, is that you get a simple client, it's portable across languages, and it's a more general solution in a sense. So let's move on to what we do at TrueLayer. So TrueLayer, we're on Kubernetes for us to deploy our services and run our services, but we have no service mesh. Therefore, we don't have any gRPC load balancing out of the box. And we have some historical precedents because we started adopting Rust last summer-ish. And at that time, our C# services used and they still use Envoy sidecar proxies to enable load balancing. And this was because there was some shortcomings in the client implementations in C#. So since we started adopting Rust, we thought this problem hasn't been solved throughout TrueLayer. Let's explore what's in Rust. So we started looking at what's out there. So the first library we found, which is gRPC-RS, implements load balancing, but it has no way of updating service IPs. So it wouldn't solve the skewed load problem where you're unaware of servers coming up. You could have an approach where the servers kind of forcefully disconnects the client, but we want something a bit more robust. And then you have gRPC Rust, which doesn't implement load balancing at all. And then lastly, you have Tonic, which implements load balancing and also has building blocks for updating endpoints dynamically or updating service IPs, which is exactly what we would want. To talk a bit about Tonic, it's fueled by Tower, and that's a nice thing because Tower generalizes a service, and from that implements all the things that are generalizable across services like gRPC, HTTP, and these things like timeouts, readiness probes, and also load balancing. So Tonic had everything we wanted: health check with readiness probes, load balancing, which uses Tower balance, which is also used in Linkerd, which shows that it's somewhat production hardened. And it also enables updating the set of servers periodically. So what came from that is we built a small library or a crate in Rust called Ginepro, which means juniper in Italian. And in that library, we enrich Tonic to achieve periodic discovery to have a fully fledged client-side load balancer. So a bit of an overview to kind of fit it in the space of the solution space that we went through earlier is that this is client-side load balancing, where we have a DNS resolver that periodically probes a headless service that we have in Kubernetes that has a service name that exposes the set of IPs that is behind that service. So essentially the set of servers that is used to update the internal load balancer within the client. So let's just look at a bit how this is updated. So it's worth noting that our DNS resolver is a thread that runs within our client. So the first thing is that the DNS resolver looks up that headless service or resolves the service name, gets back a set of IPs, and reports that change set back to the balancer. And what's nice about this is that Tonic in general, if we've given Tonic an initial set of servers, let's say 3, Tonic will, even if a server goes down or it has intermittent network failure, Tonic will keep probing that server until we say that, hey, this server is actually gone down, it doesn't exist anymore. So this means that this DNS resolver knows about our infrastructure and can also give the source of truth about all the servers that we have. So just to go through how a gRPC code is made, the client implementation will consult with the balancer about which server to call because it has all the list of servers. And it will report back to the client saying that, hey, this server is under the least amount of load, call this server. Then the client goes off and calls that server. So what we're all here for, the technical details. So let's go into a bit how we achieve this. So Tonic very conveniently has this channel abstraction, which is the means of communication that the client, gRPC client has. And it exposes us some message passing primitives that allows us to report changed sets in the servers that are available. And so here we see an example where we create that sender and that channel, and we see that we add localhost 8080 to the set of servers, and then we remove it later. So what we also did is that we abstracted away the DNS resolving and made it a part of the contract of our periodic update loop. So we came up with this lookup service that resolves the set of endpoints given a service definition. So our standard implementation will be DNS. It would get like a fully qualified domain name in Kubernetes, and it returns back a unique set of socket addresses. Now, the nice thing for us with this approach is that this lookup service can be implemented in our tests that just internally keeps a list of servers and behind the mutex or something like that. So we can test all the failure scenarios, and we can ensure that Tonic does what we expect it to do. So at the time, it helped us a lot, helped us to kind of ship this much faster because of the testability of it. And of course, our implementation or how our infrastructure is very specific. So when we open source this Ginepro, this lookup service can be implemented for other scenarios or other infrastructures. For example, just switching out of DNS solving to just calling the Kubernetes API, for example, directly. Now, how does that fit into how we periodically update our tonic client? So first, we go and we resolve all the service endpoints, and then we create a change set, meaning that this thread that keeps updating our client, hey, these are the servers available, we always keep the set that we know the client knows about. So we only remove the servers that have been removed, and we only add the ones that have been added. So we don't get this type of churn. And this also underneath, for example, the lookup service, we can hide things like DNS timeouts and a lot of these things. And then, of course, when the reporting commit is done, we've told the client, hey, this is the change set. We sleep for some time, and then we start again. So what this looks like is when fitted into a scenario, real scenario, is that we created this drop-in replacement for Tonic's channel, which we call a load balance channel. And you build it by giving it a host name and the port, and then you get the channel out of it, and you can pass it to the gRPC client as if it was a normal Tonic client, Tonic channel, sorry. And yeah, we've had this in production now since December, and it's worked out pretty well. We don't know if this is where the story ends, but at least we wanted to share with you how we've leveraged what's in the Rust ecosystem and how we were able to just add a bit of logic to get something that's production ready. Thank you.